So earlier we just completed the chapter circles. That was chapter number 17 of Concise Mathematics Standard 10th. Now we are going to continue with chapter number 18 of the syllabus, that is tangents and intersecting chords. So of course it is connected to circles only, so it is, we can say, a second part of the chapter circles. So in the second part of circles we are talking about the tangents and the intersecting chords, the properties of the tangents and the intersecting chords. So first of all we need to understand that what is a tangent. So if I have got a circle, and to the circle, if the line is passing like this, then it is no connection at all. There is no connection with this line and this one. But if it is such that it is going to touch the circle at only one point, so there is only one point of intersection between this particular line and this circle with center O. So if I take this particular point as P, then I can say that this line over here, this line AB, let's take it as AB over here. So line AB is the tangent. So AB is the tangent. So what is a tangent? A tangent is a line which is touching the circle, or we can touching the circumference of the circle at only one point. Okay? When it touches the circle at only one point, then that particular line is called as a tangent. Now if it is touching like this, touching at 2 points, 1 point over here and 1 point over here, then this particular line is called as a secant. Okay, which is forming a chord over here. This chord CD is formed over here. So this is a chord, but this line is called as a secant, and this line is called as a tangent. So tangent and secant. So tangent is the one which touches the circle at only one point, whereas secant is the one which touches the circle at 2 points. If the circle is touching the circle at 2 points, it's called as a secant, and it cuts a chord over here, CD, and when it's touching the circle at only 1 point, then it is called as a tangent. So we have over here the first property of the tangent. So properties of the tangents are what we are going to study now. So in the first property of tangent is that whenever there is a tangent, and if I draw a radius to this thing at this particular point, so if this is the radius, it is always found that they are perpendicular. That means OP is perpendicular to AB. Okay, this is the thing, that OP, that is the radius and the tangent at any point, the tangent at any point on the circle and the radius at that particular point is always going to be perpendicular to each other. So that is the theorem number 10, or we can say theorem number 1 for this chapter. And the theorem is that the tangent is always perpendicular to the radius at the point of intersection. Okay, at the point of intersection of the tangent and the radius and the tangent will always be perpendicular to each other. So that's the important part. So whenever you see a radius and you see a tangent at that particular point, then the angle between the two is 90 degrees. Now this particular proof which is given over here is just the reverse proof. तो ऐसे type का proof तुम लोग को पूछते नहीं है कभी भी exams में, because they are just taken that they are not actually proved by any kind of we would say that triangle को congruent prove किया, ऐसा कुछ भी नहीं किया. It is just they have given us that OP is the smallest side over here. It is the shortest distance between O and AB, and that is why, because the shortest distance is perpendicular distance, therefore OP is perpendicular to AB. That is the only proof what they given you. So we cannot such kind of a proof cannot come in the exam. So don't worry about the proof of this particular thing. So we have to remember that no tangent can be drawn to a circle through a point inside the circle. There is no possibility that I can draw a circle and a tangent such that the point is inside the circle. So that is not possible. Secondly, one and only one tangent can be drawn through a point on the circumference of the circle. So अगर एक particular circumference है, यहाँ पे अगर मुझे tangent चाहिए, तो that tangent will be only one. There could be only one tangent which can be drawn at this particular point. There cannot be multiples of them. There could be one and only one tangent. And secondly, only two tangents can be drawn from to a circle through a point outside the circle. So if I'm taking a point outside the circle, suppose I take a point outside the circle over here, then I can draw only two tangents. One tangent like this and another tangent over here like this are the two tangents which I can draw from a point outside the circle if this is Q. So we can see that only two tangents can be drawn. So if the point is inside the circle, I cannot draw any tangents. If the point is on the circle, then I can draw only one tangent. And if the point is outside the circle, then I can draw two tangents passing through the point and tangent to the circle. So that is the first part what you are going to have, and that is the theorem number 1. Now we see some corollary of this particular thing. And for that thing, we are going to draw a figure and understand certain things, and then we have to prove that thing. So let's see. So suppose this is a circle, and this is the point outside the circle. So I know very well that I can draw two tangents from this particular point to this circle. So we have got over here point P, this is point O, this is point A, and this is point B. If I join this like this, I know that this will be 90 and this will be 90. And if I join this, then I can see that over here in triangle AOP and triangle BOP, OA is equals to OB because they are the radii of the circle. So these are the equal because of the radii. Angle A is equals to angle B because they are perpendicular as tangents. So tangent is perpendicular to the radius, that is 90 degree. And lastly, OP will be equal to OP, that is common. So we see that triangle AOP will be congruent to triangle BOP by RHS test. Okay, it is R, H and S test by which the two triangles are congruent. Now, if this is so, then I get three CPCTs. What are the three CPCT? First thing, AP is equals to BP. That means that the tangents drawn from a point outside the circle are always equal. So that is, this is going to be equal to this. The two tangents are going to be equal because, of course, because there will be CPCT. Secondly, the angle OPA is equals to angle OPB, and angle AOP is equals to angle BOP. So this angle, this angle, this angle and this angle. So you see that you get the three corollary over here, or we can say the three important things. What you see over here is the tangents which are drawn from a point outside the circle are equal in length. First thing is that the tangents are equal in length. Secondly, the tangents subtend equal angles at the center of the circle. So you can see tangents are subtending. This tangent is subtending equal angles at the center of the circle. This tangent AP is subtending angle over here, and BP is subtending angle over here, and both these angles are equal. Therefore, AOP is equal to BOP by CPCT, and we see that the tangents are subtending equal angle at the center. And thirdly, the tangents are equally inclined to the line joining the point and the center of circle. So they are equally inclined to the line joining the center to the point. So this angle and this angle are equal. APO is equals to BPO. So these are the three corollary which we are seeing when you are taking the two tangents which are drawn from a point outside the circle. The most important out of the three is the first one, that is tangents drawn from a point outside the circle are equal in length. That means that PA is equals to PB. Very, very important. You will use this a lot many times. So that's why be more attentive when you are looking at this particular sum. If you see that there are two tangents drawn by from a point outside the circle, then the two tangents are definitely going to be equal in length. So that's the corollary over here, the three corollary which are having over here. The next one we see is one more theorem, and that is the theorem which is going to be telling us about the two circles which are touching each other at only one point. So when two circles touch each other externally or internally, so in both the cases, so we have got two cases over here. So let's see what is the case over here. We have first one wherein you have got a circle like this and a circle like this. So this is the point of intersection. This is your O, this is your O1, this is your O2, and this is your point P. Okay, or let us take it as A and B as shown in the figure. A and B. Similarly, I can have two circles like this where you have got one circle like this and the other circle is like this, and then other circle is like this, and you have got this bigger center over here and the smaller center over here, and this will be point A, this is point B, and this is point O. Okay, so this is the next part. Now it is going to be, what we are proving over here is that APB is a straight line. We are proving here that APB is a straight line. So it's a very simple proof. You just need to draw a tangent over here and a tangent over here. This is R1, this is R2. The AB is R1 and this is R2. Okay. So you can see here that this is let's say XY. Okay. So one sec. So what we need to prove is that APB is a straight line. That's a theorem. The theorem is that the line joining the centers of the circles will be a straight line passing through the point of intersection of the two circles. So it's a very simple thing. We know very well that XY is perpendicular to AP because it's a tangent. So this is 90 degrees. Similarly, XY is perpendicular to PB because again it is a tangent. So if AB 90 or AB 90 hai, तो automatically it becomes a linear pair. Therefore, angle APX plus angle BPX is equals to 180 degrees. Therefore, APB a straight line. Same thing is here also. Same steps comes here. XY is perpendicular to, so XY is perpendicular to AP and XY is perpendicular to BP also. So because you cannot have two perpendiculars at point P, so both the perpendicular are the same line, that's why APB is a straight line. So we see over here that this is how we are going to prove the thing, but of course this also proof is very silly. So normally up till now they have never asked in boards to prove this particular theorem number 11, that is, if two circles touch each other, the point of contact lies in a straight line through the center. So this is just a theorem, but normally you are not going to use the proof over here. But this also gives us one important kind of a derivation, or you can say a result, and that result is this way, that when two such circles are there which are intersecting at a point, then the distance between the two centers, that AB will be equal to R1 plus R2. Whereas if it is internally, then AB will be equal to R1 minus R2. Okay. So if it is touching externally, the distance between the two centers will be equal to radius 1 plus radius 2. But if it is staying internally, then the distance between the two centers will be R1 minus R2. So subtraction, difference between the two. So that is what we see over here. And in case of a that is the main part. That is the D is equals to R1 plus R2 or D is equals to R1 minus R2. And if AB and CD are tangents to the same circle at point P and Q such that AB is parallel to CD, then PQ is always the diameter. So if you have got anything wherein P and Q are, if there are two parallel lines which are going to be tangent to this circle, then the two parallel lines, definitely the line joining the two in point of intersection will be at a diameter. So quite easy to understand. और नहीं भी समझा तो भी वो practical है, वो उसमें कुछ फर्क नहीं पड़ता, right? So not an issue at all. And concentric circle means circles with same center. That's it. So this was the explanation about the part which we are going to do before the exercise. So that is about the tangents. So these are the thing about the tangents, and accordingly now we will be based on this three things. That is, first thing is the tangents are perpendicular to the radius. First thing. Second thing is about the corollary, that tangents drawn from a point outside the circle are equal. That is the second thing. And third thing is that the line joining the two centers will be passing to the point of contact between the two circles. That is going to be the third one, or we can say that the distance between the centers is R1 plus R2 or R1 minus R2 according to this thing. So this is what we are having in the exercise of 18A. So this is what we are going to use in exercise 18A. So we'll start with the exercise 18A. In this chapter, you have got a few more theorem, that is 3 more theorems, which will be based on exercise 18B, and of course 18C will be your homework part. So let's see. Let's start with exercise 18A. It's given that the radius of a circle is 8 centimeters. Calculate the length of the tangent drawn to a circle from a point at a distance of 10 centimeters from its center. So we have got it something like this, that this is a circle and this is the point over here, and which is radius is equals to 8 centimeters, and a point is at 10 centimeters over here. So this is at 10 centimeters, and you are going to draw a tangent like this. You need to write the distance over here. So it is OPT. So accordingly, you know that this is what you need to find out, PT. When this is going to be 8, this is going to be 90 degree. So it's simple Pythagoras theorem. So we have over here that OT is perpendicular to PT because tangent property. Therefore, triangle OTP is a right angle triangle. Therefore, PT square is equals to OP square minus OT square is 10 square minus 8 square is 100 minus 64 is 36. So PT is equals to 6 centimeters. So the length of the tangent, so tangent is equals to 6 centimeters. Calculate the length of the tangent is 6 centimeters. We now see question number 3. It is this way. There are two circles, one here, another like this, and then there are tangents like this. We got this as A, P, B and O. Q. Two circles touch each other externally at point P. Q is the common tangent between for them. Prove that QA is equals to QB. To prove that QA is equals to QB. Okay. You want to prove that this is equals to this. This is what you need to prove. Very easy sum. It's an easy sum, and that's why the proof of such kind can be asked. So otherwise you'll say the proof sums so cancelled. No, such can are not cancelled. They are very easy. It's just a two-step one. Can you think it over? Okay. We'll be using the corollary of the tangents. A tangent drawn from a point outside the circle are equal. That means QA and QP are the tangent to this circle. So we know that proof will be QA is equals to QP tangents drawn from a point outside circle. So we know that the point outside circle are equal. So accordingly they will be equal. We also know that QB is equals to QP. Again the same reason. This line will be equal to this line because they both are to the same circle. So if QA is equal to QP and QP is equal to QP, that will be QA is equals to QB. Hence proved. Very easy. 2 steps. Right. So this was sum number 3. Now we move on to sum number 5. Two circles of radii 5 and 3 are concentric. Calculate the length of the chord of the outer circle which touches the inner circle. So first of all, we need to understand the question and draw a figure based on that. Once you draw the figure, then the sum is very easy. Okay. It's here that there are two concentric circles of radii 3 cm and 5 cm. That means there is one circle over here which is of radius 5 and one circle which is inside over here which is of radius 3. So we have over here that one is radius 3 and one is radius 5. You have a chord which is of the bigger circle which is touching the smaller circle. We know here that this radius over here is 5 and this radius over here is 3, and we also know that this is a tangent to the smaller circle, hence this will be 90 degree. See how simple it is. Yes. Calculate the length of the chord. So you know that chord which is touches the inner circle means it is tangent to the inner circle. So it is perpendicular. So this particular thing is a right angle triangle with O, A, B and D. So accordingly we know that OD is perpendicular to AB, tangent property. Therefore in right triangle AOD, AD square will be equal to OA square minus OD square. This is by Pythagoras theorem. Accordingly we have is 5 square minus 3 square is equal to 25 minus 9 is equal to 16 is equal to 4. So AD is equal to 4 centimeters. Therefore AB is equal to 4 into 2 is equal to 8 centimeter, because perpendicular from center bisects chord. That will study it in the 8th standard. The perpendicular drawn from center to the chord bisects the chord. That is what we are using here. Hence, if this is 4, this will also be 4. Therefore, AB will be equal to 8 centimeters. That was question number 5. We now move on to question number 7. Now question number 7. If the sides of a quadrilateral ABCD touch a circle, prove that. Okay. So sum number 7. This is the circle and these are the sides. Okay, whatever may be the figure over here, I just, yeah, quite similar. Yeah, so it is A, B, C and D. We'll take this as P, Q, R and S. The point of intersections of the circle and that particular thing, tangents, so that will be, we need to prove that, AB plus CD is equals to BC plus AD. AB plus CD is equals to BC plus AD. Yeah, very simple. Yes, it is simple. Now, first of all, let's see from point A there are two tangents, AS and AP. From B there are two tangents, AP and PQ. So this is equals to this, this is equals to this, this is equals to this, and this is equals to this. So we have over here proof. AP is equals to AS, BP is equals to BQ, then we have CR is equals to CQ, and then we have got DR is equals to DS. Okay, AP, AS, BP, BQ, CR, CQ, DR, DS. All these are tangents from point outside circle are equal. Now let's add all of them. So what we have? AP plus BP plus CR plus DR is equals to AS plus PQ or DS plus BQ plus CQ. What is AP plus BP? AP plus BP is AB. What is CR plus DR? CR plus DR is BC or CD. AS plus DS is AD. BQ plus CQ is BC. Hence proved. Yes, done. Utna hi tha. Okay, so you can see very simple. It is a very simple sum. भले proof sum है, फिर भी बहुत easy है. So such sums can be asked. So be prepared for that. So this is very easy. You're just going to use one single property that the circles or the tangents drawn from a point outside the circle are equal. We now move on to sum number 9, but I think I'll take it in the next video. Yes.